Let's continue with chapter 3 in Ohm's applications. So we saw how we can use Ohm's applications from tables or graphs. Now we are going to see how we use it in the lab. So right here we are using an ammeter to measure the current in this simple circuit. We have the power supply set at 15 volts. We have our load, in this case being a resistor, and then we have the ammeter in series with the loop that we are measuring the current. This is very important. You see how the ammeter is part of the circuit, otherwise it doesn't measure anything. So right here they're asking you, what would the ammeter read? What would the current of this circuit be? So they give us the color value representation of the resistor, and we are supposed to know what the green, the blue, and the brown and the gold stands for. So in this example right here, that represents for a 560 ohm resistor with a plus minus 5%. So when they're asking you what is the ammeter reads, an ammeter measures current. So what they're asking you is what the current is for that circuit. So we write a definition, we write that the current, we write at Ohm's law, where we say current is equal to voltage over resistance. We have the voltage, we have the resistance, so we just plug in, we get our value, and we can write it. We can do a rough estimate by saying 27 milliamps, or we can be more specific and write 26.8 milliamps. So for the test, for the quizzes, we are going to be more specific, and we are now going to be rounding up to the next integer. We are going to be saying 26.8 milliamps unless it is otherwise stated. Okay, very simple. Now we have discussed Ohm's law. We are going to move into energy and power. Energy, we have used it when we define what was voltage. If you guys remember, voltage was defined as being energy or work over charge. Right here, work is defined using physics, where we say that the work is equally to the force applied to this block times the distance the block is moved. That is the definition of physics. So work, it is force times the distance the block was moved. The units are joules. Here we continue with a little bit of background in physics, saying that a joule is equivalent to the work done when a force of 1 Newton, equivalent to this apple, travels a distance of 1 meter. That is the representation of a joule. Its symbolic representation in formulas, it's a capital W, not to be confused with watts for power. So it is very important here to make a distinction. So work, it's very related, is very close related to energy. So energy is the ability to do work, and the units are in joules, while power is the rate at which energy is used. We will define it in a couple of slides ahead, what is power. But power and energy are very close related, because energy is just the ability to do some work, and power is the rate at which energy is used. For example, they are giving us an example here, where they're saying that we have a distance of 5 meters and we are going to apply a force of 400 newtons. We just must multiply it, and we get the work or the energy required for us to perform this, to move this block for 5 meters. Okay, So right here, we are going to define what power. Power is the rate of doing work, and as we mentioned before, anything that has the rate in it has to have time involved. So right here, power is defined as work divided by time, which is going to be joules over seconds, where work is going to be in units of joules and time is going to be in units of seconds. So the unit of power is watt. So here is where the confusion can start. Work, capital W, and watt for the units of power. So we are going to use lowercase w for watt and capital case W, capital W for work. So we write a little distinction there. Okay, and so power, the units are watt. We are going to represent it as capital lowercase w, but its definition, it is energy or work over time. Work is going to be represented as capital W. So right here they are giving us an example of an application. What power is developed if the box in the previous example is moved in 10 seconds? So in the previous example, we calculate the energy needed when they're giving us the distance and the force applied to that box. And now we're going to find how fast we can use that energy. And in essence, they are saying that we can use it in 200 watts. Just like we use the definition for voltage and the definition for current, it is important to understand that this is the definition for power. However, we have something called Watt's law. And Watt's law, what it does, is going to relate Ohm's law to power, so that we can go from voltage and current to power. So let me show you how that is done. So Watt's law is the relationship between Ohm's law to power. So power using Watt's law is said to be power is equals to voltage times current. We can derive this from its definition. We know that the definition of voltage was work over charge, and the definition of current was charge over time. So we can say we replace its definition by, then we cancel the charges and we get work over time, which is actually the definition of power. So it is important that Watt's law is what link Ohm's law. And that is important because sometimes people talk about what is the power rating, or they give you the power value of a resistor. So you, from power, you can find voltage, you can find current, you can find resistance. And the way you would do it is you just would put in this format, and then you can solve for B using Ohm's law, and then you plug it in here, or you can solve for I and plug it in here, if that would be the case. We are going to do in the example and problems section for this chapter, I will do examples where we use Ohm's law to find Watt's law, or we use Watt's law to find quantities needed in Ohm's law. So it is quite useful, and we'll see how that works. Right here, energy and power. Another measurement that we are going to be getting familiar with is kilowatt hour. So kilowatt hour, it is a measurement of energy other than the joule, standardized in a lot of electrodomestics and different applications of power here. where the ratings are going to be in kilowatt hour. Like for example, when we get an electric bill, we get charged for kilowatt hour usage. When we buy a refrigerator, its rating is in kilowatt. How many kilowatt hour uses? And that's how it gets rated. That's how it goes, if it is environmentally friendly or if it is just a heat hazard, right? So don't get thrown up by the fancy kilowatt hour. It just means 1,000 watts per times hour. That's all it means. We are going to do an example right here so you can understand what it means. So they say there are 3.6 times 10 to the 6 joules in 1 kilowatt hour. So that is the exchange rate that you can use. That is your link to go between joules and kilowatt hours. Like for example, in the homework, I give you something in kilowatt hour and you are asked to find the power. So then you can move from there into joules to have the work, and then if you're given the time, then that is your power right there. But like I said, it is a convenient measurement for electrical appliances. So here is the example. What is the energy used in operating a 1200 watt heater for 20 minutes? Okay, so here is the trick. You have to first take the watts into kilowatts. So basically you're going to take the watt into kilowatt, which means you go from regular value to kilowatt, divide by 1,000. And then you have to take the minutes. In this case, the time is given in minutes to hours. So you have to say 20 minutes to an hour. So you can say 60 minutes in 1 hour to find the 1/3 of an hour. Then you just multiply them, and that will give you your rating for that heater. So you'll be use 0.4 kilowatt hour. And we're going to do an example then where you're going to find out what is the cost of you running that heater for those 20 minutes.